So let's look at some animations that can go along with Chapter 2. Here we have compression work. And so work in a compression process is evaluated by the work in its integral through volume 1 to 2, and then pressure D for the derivative and then V. And so you have the value of the work depends on the process, right? Because we're concerned about the process. The negative sign is associated with compression work since the energy transfer is to the system from the piston. So we're going to look at the compression process. So if we have a constant pressure, right? So ISO, so constant pressure process. Let's look at what that looks like. Constant pressure process, the shaded area under the process path is equal to the magnitude of work for the constant pressure compression. We'll see it one more time. So you see it up here on this PV, right? It's equal. So you've got V1, V2, X1, X2. So it's equal to that. Let's look at constant volume. So see, it's going down. So we have a constant volume. We had a constant pressure where P is right here, and we just stayed on the constant pressure. Let's see if we can. Yeah, where we stayed on the same pressure line. But here it's constant volume, so we went down, but we changed in pressure. So we had P1 and P2. And then constant temperature is, there you go. So the reason why this looks like this is because what we're looking at right now is a PV diagram, pressure volume. You see that on the XY axis. This is actually an XYZ chart. It's called the PVT chart, and we will be using it an abundant amount of time. We are really going to go and delve into it when the time comes. Anyway, on the x-axis, it's T. And so therefore, the process path that you take is actually for temperature. And so that is a constant temperature. Let's look at expansion work. So that was compression. It's looking at expansion. And so again, it's just the opposite. Instead of compressing, we're going to be expanding. And a positive sign is associated with expansion work since the energy transfer is from the system to the piston because we're concerned about the system, right? So we are doing our work. It's positive. Constant pressure process. Let's look at that. There you go. So constant pressures, you see we have pressure on the y-axis and it's staying the same. No change there, but there is a definite change in volume as you can see. And then this is a constant volume. What's going to happen? It's going to go straight up, but we're going to have an increase in pressure. And then constant temperature, how is that going to go? That's right. It's going to go back just down the other side. Okay? So the same thing, let's look at total energy. Okay, so the total energy we talked about is the sum of the internal energy, kinetic energy, and potential energy. E equals U plus KE plus E. And in the absence of friction, of course, because we assume that it's frictionless, the total energy and internal energy of the ball remain constant because that's our assumption. Energy is converted between kinetic energy and potential energy, with any increase in kinetic energy resulting in a decrease in potential energy by the same magnitude, right? So if we're increasing kinetic energy by 3, then PE is going to decrease by 3. The case in which frictional effects are present is considered in chapter 5, but right now we're looking at it as far as frictionless. So let's look at that. Do you see how KE and PE are moving? And then because it's frictionless, internal energy is staying the same and total energy is still staying the same. But we are converting between KE and PE, and we are talking about frictionless, right? No friction. That means that that we are not taking into account anything that's happening or any losses or gains when we're talking about the ball moving on the field or on the plane. All right, so let's talk about the heat transfer modes. So here we have heat transfer modes are conduction, convection, and radiation. Okay, and so here the symbol Q denotes the amount of energy transferred across a boundary of a system. Okay, and so Q with a dot, I'll probably refer it to just Q dot, is heat transfer to the system, or Q dot is heat transfer from the system. Okay, and then alternatively, heat transfer direction may be indicated by an arrow that is considered positive in the direction of the arrow. Right? So if it's going out here, it's positive out. So you see Q is moving in, and it can denote both of those. Okay, so let's look at conduction. Okay, conduction is the transfer of energy from more energetic particles to a substance to adjacent particles that are less energetic due to interactions between the particles. Energy transfers by conduction take place in solids, liquids, and gases, of course. Right? And so here we have, using alternative sign convention, positive heat transfer is indicated by the arrow direction. And then Fourier's law states that the rate of heat transfer across any plane normal to the x direction. So when we talk about normal, we're talking about a plane, like an xy plane. So normal to the x direction, Qx, is proportional to the wall area A and the temperature gradient x direction, which is this formula down here. And then K is a property called thermal conductivity. Okay, so we will be able to find those as well. So these are a lot of formulas. It's basically just saying this is how we can compute conduction. And then let's look at convection. Convection is the energy transfer between a solid surface at a temperature and an adjacent gas or liquid at another temperature. Convection is a combined effect of conduction within the fluid and bulk motion of the fluid induced by wind, for example. And then here's the formulas as well. And then when we're talking about radiation, of course, we start talking about the space, the space realm. Thermal radiation is emitted by matter as a result of changes in the electronic configurations of atoms or molecules within. Radiation requires no intervening medium to propagate. It just happens. The energy is transferred by electromagnetic waves or photons, right? Okay. And then we start using the Stefan-Boltzmann constant and things like that. But we'll get into all of these, and it'll make a lot more sense when we start actually working these. This is just to kind of give you a visual representation. Okay, there you go. And so you see the little bit of changes. It's kind of like going from like a micro to a macro scale. Okay, energy balance of a closed system. So here is state one. At its initial state one, a closed system has energy. Numerical values of energy are determined relative to reference state, usually as 0. So this is just state one. This is the beginning state, and then we're going to show you kind of how it works. So this is state one, and then what I want you to do is see state two, and then we will look at the process. So this is where we start. This is where we end. Okay, it's the exact same. This is where we started, or this is where we started, and this is where we ended, so E2. But look at the process in between. So we've got heat transfer coming in. We've got some moving boundary work. We've got some shaft work, and we've got some electrical work. So the only ways energy can be transferred across a boundary of a closed system are by heat or work. Remember, heat or work. That's the only way we can get energy across that boundary. Okay? And so then we can just end up here. And then here's a little summary to show. So we talk about total energy, total KE, the change in KE, the change in PE, the change in U. And then we're talking about the formula here. So the change in KE plus the change in PE plus the change in U is equal to Q minus W. So heat transfer minus work. Okay, and then let's look at some power cycles. We briefly talked about these. You can kind of see them. So the definition of a power cycle is a system that undergoes a cycle that delivers a network transfer of its energy to its surrounding while communicating thermally with two bodies, one hot and one cold. So you see the hot, you see the cold, and we have a hot body coming in and a cold body coming out, and then we have work cycle Q in and Q out coming out. And then you see here we've got thermal efficiency. You see that little N, that denotes our efficiency. And so then you've got some formulas here to calculate that efficiency of this cycle. And then we can do maximum performance as well, right? And so that's efficiency max. And then we start talking about TH and TC, right? Okay. And then let's look at refrigeration cycles. We didn't too much get into this. We're just going to kind of look at them. Okay. And so you see the refrigeration cycle is the one where you have a cold body coming in and a hot body coming out, because the refrigeration cycle is a system that undergoes a cycle that transfers energy by heat into the system from a cold body and discharges energy by heat transfer from the system to a hot body. Network input to the cycle is required to accomplish these energy transfers because we know that naturally heat flows from hot to cold, but we have a refrigerator. So we're having to put work in here to expel heat out. Anytime you see the refrigerator, don't think that your food is being cold out. Think that all of the heat is being forcefully removed from it. And then we start talking about performance. Okay, so we've got the coefficient of performance. It looks like a B. And then you've got some formulas there. And then, of course, you've got maximum performance as well. So you have performance because you have work going in. That's something that we are performing. And then when we have just the other, we have efficiency. Okay, but you also do have the max for that as well. And then let's look at the heat pump cycle, and that'll be it for chapter 2. Okay, and so then we have a heat pump, we have work coming in, you have cold body coming in, and hot body coming out. And so the heat pump cycle is a system that undergoes a cycle that transfers energy by heat into a system from a cold body and discharges the energy by heat transfer to a system to a hot body. Network input is required to accomplish this, right? So you can think of this kind of like the refrigeration. We'll get into the differences when we start actually working these, but this is another type of it. So again, we have that performance as well, but it's denoted by this coefficient of performance Y. And then again, you have that max as well. So these will start making much more sense when we start actually calculating them and getting into the specific portions of it. But hopefully now you can kind of see how just the heat is flowing, what work is, what heat is, where we get our heat, what the first law of thermodynamics is, how we're converting or conserving our energy, that we're not creating, things like that.